The last person between you and the questions. Okay. So my name is Ken Curitan. I'm going to be talking to you about the integration of system dynamics with SysML and model-based systems engineering. I'll be the first to admit I am not an expert on system dynamics. Dr. Taylor could not be here, but I am an expert on resilient systems design and complex systems design, and have done quite a bit of work on integrating that in a model-based systems engineering environment. What we really wanted to do is to tackle some issues that have been plaguing model-based systems engineering for some time. How do you deal with complex systems, especially complex adaptable systems with machine learning, human in the loop and the control loop, things of that nature, where the results are a bit unpredictable or at least difficult to predict? How do I deal with the need for resilience? In other words, I need to achieve the basic objective of providing some capability in spite of adversity. How am I going to go about anticipating and avoiding it, withstanding it, or recovering from it? How do I model those things when there may be considerable uncertainties in the adversaries? So here's our goal. We wanted to take the beauty of system dynamics, a proven methodology, incorporate that as a method in MBSE using SysML. And the idea is to help to emphasize developing resilient systems, something that is able to deal with a large number of adversities. So here's the beauty of SysML. It gives us a standardized modeling language. You all know that. And it has a number of different ways of representing these items. Highly useful in model-based systems engineering, so we can move away from the old document-centric approach into something that is, better integrated. You have something that's able to recognize updates. And the idea is that I can use the models to help communicate, to help train, to help understand what's happening in the future. So system dynamics is great at generating a highly interconnected system of differential equations to represent the system's behavior. These can be solved using numerical methods, relatively straightforward. In other words, it tells you, here's where I am. This is where I am today. This is how I got there, and this is how I'm potentially going to go in the future. If something changes, if nothing changes, and the like. And the whole idea is it uses feedback loops, stocks and flows, time delays, behavior over time diagrams, and a number of other methodologies that are well proven. And those can be easily moved into behavior diagrams. Now, the challenge of trying to integrate all of these things is in complex systems, things move. It's very difficult to predict the behavior. So the standard problem we had with, say, SysML version 1 was it was very good at capturing structures. It was not very good at capturing all behaviors. Now, SysML version 2 has improved this. So for those behaviors you can predict either numerically or stochastically, you can represent that. But how do you deal with uncertainties? That is something which we wanted to explore. So the idea was if we integrated system dynamics and expressed things in terms of SysML version 2 for model-based systems engineering, we will get a more holistic view. This is the structure. This is the behavior that we know about or at least can predict. This is how we're going to be able to represent that, especially in the face of uncertainties. So what we did was we started looking if we couldn't take the basic system dynamic concepts, stocks and flows, create activity and block diagrams using those. The feedback mechanisms, since system dynamics highly incorporates various feedback mechanisms, put those in as dependencies and control flows in SysML. And then to take the first order differential equations from system dynamics that need to be solved and put those in parametric diagrams. So we looked at a number of different tools and languages for doing this. These are just a few. I do not want to get into a tool worship session here where I jump in and I say, this is my tool, this is the answer to all problems, use my tools and your problems go away. These are just indicative tools, Modelica, Simulink, which we could use to represent system dynamics and then create the appropriate SysML diagrams with those. Now, when we get into resilient systems design, this is where much of the fun begins, because we've defined in the Resilient Systems Working Group, of which I'm the chairman, the ability of a system to be able to provide some required capability. This is what I really must have it do. In Department of Defense terminology, this is my threshold capability. Yes, I have objectives. I have more capability that I desire, but I have to do this under adversity. These adversities may be known, they may be unknown. So what am I going to do with this? How am I going to go about avoiding adversity? How am I going to withstand it? How am I going to recover from all of those? And then how do I model that? Now, through a considerable amount of effort, we've developed a section in the systems engineering body of knowledge, the CBOC, which talks about how you model resilience using system dynamics and other methodologies. So if using system dynamics, we can create the appropriate SysML diagrams to represent vulnerabilities and potentially design mitigation strategies. Here's what we really want to do, though. Ask what ifs. What if this occurs? What if that occurs? That's difficult to do purely in SysML. So what we can do is we can use system dynamics to simulate some of the adversities, how we would go about adapting the system to that, and the recovery processes, and then represent that in SysML as well. So the big advantage here is to be able to deal with things that you may not see just looking at or creating the diagrams. How do you go about simulating all of this to create a more resilient systems design? Now, if you do this, we see some huge benefits. Number one, we are combining both the structure and behavior perspectives in such a way that it is able to deal with uncertainty. We can actually go in there and ask these what if questions and get better prediction of system behavior before, during, and after adversity. Again, with the goal of dealing with the kind of things that you may not be able to see as you create your SysML diagrams, or if you look at them or you apply them. You can, using some of the modern techniques, such as, oh dear, may I use the words large language models? Okay. You can start doing a bunch of what ifs using some of the modern tools and to be able to develop better unified models. And you can do this in such a way that you can ask your stakeholders, what if this occurs? This is how the model says things are going to potentially occur. Well, that's unacceptable. I need changes to that. Well, why didn't you tell me up front in your requirements? I didn't know I needed to tell you about that. So the big advantage that we find is to be able to show people what ifs and to try and give them an opportunity to say, under these circumstances, under this potential future, this is how the system might behave in the face of adversity and in face of complexity, in the face of various things that we don't know about. This isn't perfect. We do not know yet how to model unpredictable behavior. That does not seem to be possible at present. But for those things where we at least can simulate and look at things through system dynamics and other mechanisms. We can represent it in SysML and then use it in MBSE, both as a design tool and as a communication tool. And that's our goal. Okay, so I'm all done. Okay, yes, I'm bringing them up.
Everybody come on up here. Troy and I are always amazed that boy, we did a really good job on organizing this sequence, didn't we, Troy? It's like, so I guess, I don't know that Troy and I ever, Troy, grab your, I guess we're gonna need some microphones. Go over and grab those microphones, guys. Well,